on and cover the rest of those forces about a couple of things, and that is something called the net force. This is the vector sum of all the forces. On a particular object. All right, now when I say vector, a vector is something that has what we call a magnitude and a direction. All right, so for example, a certain vector would be like our velocity. And if I'm traveling, what's this, to the left with a, or I'll do it to the right. If I'm traveling to the right with a certain velocity, say 1 meter per second, 1, 2, 3, 4, that's about a velocity of 1 meter per second. I have a speed, a magnitude of that velocity, which is 1 meter per second. That's just the value of whatever the quantity is. And then I also have a direction. And in this case, the direction was what? To the right, right? So I have a magnitude and a direction. So whenever I say vector, that's all that means. It just, the quantity has a value and it has a direction. And some quantities are vectors and some are not vectors. So for example, a force, vector or no? A force is a push or a pull. Does it have both a quantity and a direction? Yeah, a force is a vector. What about velocity? Vector or no? Does it have a direction?
Yes.
Yeah, that's the one we just did, right? What about acceleration? Vector or no? Yes, no? Oh, what's the word? Acceleration, right. Does it have a direction? Yes, it does. Or how about mass? Does it have a direction? No. So a mass isn't a vector quantity. There are other quantities that aren't vectors that don't have directions, like charge, right? No direction. Mass. Time, does it have direction? No, not really in the way that we think about it, right? It sort of progresses as time goes on, but it doesn't have a spatial direction. All right? So when I talk about vectors, that's all that means, is it just a quantity that has a direction. And when I talk about the vector sum, I'm going to have certain directions be positive and certain directions be negative. And in our world, mathematically, the directions that we take to be positive are up and to the right. So when we're traveling to the right, that's positive. When we're traveling up, that's positive. So if I were to draw an axis, or a coordinate system, it looks like this. To the left, or excuse me, to the right is positive, and up is positive. In particular, we call this the x direction and that the y direction. But really all you need to know is that to the right is positive, to the up is negative. Or excuse me, not negative, positive. So up is positive. And then to the left is negative, and down is also negative. And in particular, these are the negative x and negative y directions. So for example, if I have vectors, say I have an object that's right here, and it has several forces acting upon it. I have one force that is, say, I don't know, 10 newtons in this direction, and then another force, hey Dwana, I have another force in this direction that is 5 newtons. To take the vector sum of these would be to say, I'm going to take the sum of this vector and this vector. So this vector is positive or negative? It's to the right. So in our right-handed world, like literally we live in a world where we use a right-handed coordinate system. You don't need to write that down. But where we take right to be positive and left to be negative. All right. This vector has a sign of what? Plus or minus? Minus. I haven't drawn minus here, but it's inferred because left is to the left. And we, I don't know, left is negative or whatever. All right, so my net force is what for this object? Right, it's 5 newtons to the right. So my net force, F net, which is the sum of all the forces. This is a symbol, the Greek letter sigma. It just means to sum up something. So tri-sigmas, y'all should be called the sums. Any other tri-sigmas? No, there are two of you. Y'all should propose that to your sisters. Some. All right, so the sum of the forces here would be plus 10 newtons minus 5 newtons, and so my net force would be 5 newtons. Is that net force to the left or the right? It's to the right, so we know this is positive. It comes out as positive, and it's to the right. All right, so that's one thing I want to point out is the net force, which is just the sum of all the forces. But not just any old sum, it is the vector sum of all the forces. All right, the next thing I want to point out is a free body diagram, which I've already drawn here, and it has a fancy name, but it's not really that fancy. A free body diagram. Your book uses these a lot. I think they might even describe a free body diagram. But a free body diagram is just a picture of whatever object you're talking about with all the forces drawn on it. So I've already drawn a free body diagram right here. I have some object, a block or a box or whatever, and I've drawn the force there and the force there. That's all it is. It's just a diagram that has all the forces that are acting on that particular object. This is a free body diagram. Okay? And we'll draw these as we go about. And in your book, they draw a lot of free body diagrams. Particularly, they draw free body diagrams that we'll look at later of the human body and the forces that are at play there. Okay? So two terms, net force and free body diagram. Sorry, I meant to do those last time before we got into forces. Let me just sort of recap quickly. We've gone to types of forces. One of those was weight, which is the force of gravity on an object. We can find the weight by multiplying the mass times the acceleration due to gravity on Earth. And so, for example, a typical person is about 70 kilograms, so they're about 700 newtons. We also talked about the normal force. The normal force is a response to which of Newton's laws? Or is an illustration of which of Newton's laws? Right, the third law, right? For every force, there's an equal and opposite force. So, for example, this desk has a force weight pulling down upon it, and then likewise, the floor is pushing back up with the same force, but in the opposite direction. So there's an equal but opposite force that's at work. And that's an application of Newton's third law, which of course you all went out and told your friends, right? Did you know that there can never be a single isolated force? Did you go out and tell your friends? Yes, some of you did. Okay. I think that's kind of far out. Like, it seems very philosophical that you can't have an isolated force, but in fact it's true. All right. Oh, and look here. We actually drew a free body diagram here. So this is a free body diagram illustrating that normal force. All right. Let's do just a few questions. Some of these are going to be new questions and some of the old questions. I sort of want to give you a feel for what the quiz will be like. These aren't the same questions as on the quiz, but just sort of give you a feel, because I know people get a little anxious about quizzes and stuff. So let's just try a few of these questions. First of all, Newton's first law says that if an object is moving, it will slow down unless a force acts upon it. Is that A, true, or B, false? So these aren't your quiz questions. These are just sort of quiz-like questions. In fact, these are from some old quizzes that I pulled out. I'm going to stop at 35 seconds. Remember, if you don't know the answer for sure, just guess. You get credit for guessing, too. Is that right? False. Yes, false is correct. That is not what Newton's first law. It says that an object will continue in motion unless a force acts upon it, that it won't slow down. Although that's what people used to think, and that's what a lot of people today think, is that objects naturally slow down and come to rest, because that's what they observe in everyday life, because of certain forces that are at play. Newton's third law says which of these? Just a few more seconds. I'll stop at 30. 30. Remember, you can ask your neighbor when we're doing clicker questions. Not during the quiz or exams, but during this. All right, A is right. A is right. Which of these would be the first law? C is the first law, and the second law is B, right. All right, a block has 2 ropes attached to it, as in this figure. A person pulls the left rope with a force of 10 newtons. A person pulls the right rope with a force of 20 newtons. What is the net force on the block? All right, I'm going to stop at 33 seconds. 33. Oh. Excellent. Do y'all want a joke then, since you got 100%? You don't always get a joke if you get 100%. This is a pretty easy question, but I'll give you one anyway. All right. This one's kind of crude. What's the worst thing about living on O Street? I don't know what. You gotta walk a whole block to pee. Gotta get it. That's like a 3rd grade joke. You throw it out on a 3rd grade playground, and they're going to be rolling in the aisles. Okay? All right. By the way, what is the acceleration of this block? If I want to know the acceleration of this block, I know the net force. I know the net force is 10 newtons to the right. Oh. Back to this. 10 newtons to the right. I don't have a pen. Sorry. Anyway, I know that my force is 10 newtons to the right. So what is my acceleration? Okay, well, I want to go with Newton's second law. I know that F equals ma. I know that my acceleration is, my force is plus 10 newtons to the right, so it's positive. My mass is 10 kilograms. And this, I want to know what is my acceleration. What's it going to be? No. All right, 10 is equal to 10 times what? 1. Right. So if I want to find this, so if you've been a while since you've had algebra, you would divide both sides by 10. That would cancel that out. And it would have A is equal to 10 over 10, which is equal to 1. All right. Our algebra won't get too much more complicated than this as far as math, but if you have trouble with this, please come see me. We can work it out in 10 minutes. You'll be good to go. Okay? All right. Okay, we haven't covered this, but you should have read about it. The force due to the muscles in this figure, Fm, produces which kind of force? So there's this force right here, and it's like the force of your, what's the muscle called that pulls you up? Erector spinae? Yeah, spinae. Yeah, so what is the direction of the torque? Is it clockwise torque, counterclockwise torque, or no torque at all? That causes me to go like this and stand up. The muscle that pulls me up. The erector spinae. Spinae or spiny? Spinae. I have an anatomy book, and I've been trying to read it to sort of know what y'all know, but it's a lot to read. It's a big course, huh? Anatomy? Yeah, okay. All right, I'm going to stop at 55. That's right, clockwise is correct. So I know this, I imagine, we'll talk about torques in a bit, but I imagine that I have this thing that's rotating about the axis of rotation, And if I pull up on this, it's going to cause it to move in a clockwise direction. We'll talk about that in a while. Muscles are connected to the bones at least 2 points. The point attached to the bone that moves is called what? The origin, the torque point, the axis of rotation, or the insertion point? The point that moves. Again, not something we've covered. We'll cover it today, but it was in the chapter. I'll stop at 30 seconds. Y'all got this down. That's right. D is right, the insertion point. That's the point that moves. The point that doesn't move is called the what? Origin. Very good. Did y'all get that from the book, or you already knew that? You already knew that, right? Yeah, that's good. So you know what a third of this score? It'll be super easy for y'all. The physics stuff, hopefully some of that will be new. But a lot of it we're into anatomy, which most of you have had. All right. Newton's second law is called the law of what? Reaction force, acceleration, or inertia. Stop at 25. Sorry. C is right. Very good. Remember, the third law is the law of reaction, and the first law is the law of inertia. There is no law of force. Just one or two more. Newton's second law says a net force causes an object to travel at an increasing velocity. Is that A true or B false? I'll stop at 28. 28. All right. A is right. I worded this a little bit differently. Right. What does increasing velocity mean? Remember we talked about distance, velocity, and acceleration. Was that wrong? What did you say? Acceleration. Acceleration. To accelerate means that our velocity is changing. So I changed it up. Like if I would have said travel at a constant acceleration, everybody would have put true, right? That's what Newton's second law says. But I'm saying the same thing here, that a net force causes your velocity to increase. All right, remember the incorrect law of motion was that a constant force causes a constant velocity? That's incorrect. A constant force actually causes an increasing velocity, which is the same as saying that it accelerates in a positive direction. That's all. So that's just sort of a little preview. It's not the questions you'll have in your quiz, but most of y'all did pretty well in that, right? Like you feel more comfortable about the quiz? Yeah. Quiz is not a big deal. I don't want y'all to sweat it at all. I told y'all I'm working on a master's now. Did I tell y'all this? Yeah, so I have these online classes. I take a lot of quizzes. I took a quiz this morning. You know what I made on it? What do you think I made on it? 100%. Yeah, seriously. That's pretty good, huh? You can't really get better than 100%. Are y'all proud? Yeah, I'm glad. All right. It was like open book, and you could use whatever you wanted. The questions are super easy, so I'm not really that good of a student. All right. Let's look at some more different types of forces. We're going to look at friction. And then that's it. We'll do friction. Remember, we've already done weight and normal force, and now let's look at friction. I think friction is terribly interesting. A lot of cool applications and a lot of things about it that are interesting. We have two types of friction. Right? We have static friction. have kinetic friction. And then also, just in general, let me see. This is the force between two surfaces. Either moving or not moving. Well, I'll show you this static and kinetic. The force between two surfaces, it always opposes the direction of motion. Right? The frictional force is the force between two surfaces. Right? I slide my hands together, or if I push an object across the floor, I experience friction. And it always opposes the direction of motion. So for example, if I pull the scale in this direction, what is the direction of the frictional force? It's in that direction. Right? So imagine in your minds, you can create that free body diagram. I have two forces acting on this. I have a frictional force in that direction, and then I have another force that's pulling in this direction. Now my net force is in this direction, but I have an opposing force as well in that direction, which is causing it to slow down. All right, there are two types of friction. Static friction is the frictional force between non-moving objects or stationary objects. And then we have kinetic friction is between sliding objects or moving objects. Right. One more thing about friction, then we'll return to static and kinetic friction. Friction increases when the normal force increases. Okay, so say for example, see wrong arm and anything else. Alright, go out. I want you to pull on that here. That's pretty easy, right? It slides it across the desk. There is a frictional force between the ruler and the desk, correct? If I want to increase the frictional force between the ruler and the desk, there are a couple of things I could do. I could change the surfaces. I could take this surface and put sandpaper or something on it, and that would make it rougher, and it would just cause the frictional force to increase between the ruler and the desk, just because you changed the surfaces. So you can change the surface, and that changes the frictional force. What's the other thing I can do? Okay, what am I doing when I add weight? What am I increasing? I'm increasing what? The normal force. Right, I increase the normal force. And so, for example, no, I'm going to try to get in a second. If I push down, I'm pushing down with a certain force, and that's causing the normal force to increase. So the normal force on this is increasing. Okay, so if you increase the normal force, that increases the frictional force. Okay? By the way, that is why whenever you want to move something heavy, how do you push it? Do you push it like this, or do you pull it like this? If you want to move something that's really heavy. You're going to pull it. The reason is if you pull it, what are you doing to the normal force? Like this. Decreasing. I'm decreasing the normal force because basically I'm pulling this up a little bit and causing the normal force to decrease. Whereas if I push down like this, I'm increasing the normal force. Right, so the frictional force is on the surfaces and then also the normal force. And if I increase the normal force, then I increase the frictional force. We can write this mathematically. the frictional force, the script F, is equal to something we call the coefficient. This is the Greek letter mu times the normal force. This is the coefficient of friction. It describes the surfaces only. And so it's different for different surfaces. So, for example, ice, big or small coefficient of friction? Small. It's really slick. So very little friction, very small coefficient of friction. Sandpaper, a lot bigger coefficient. Rubber, depending on if it's wet or not, has a high coefficient of friction, right? And then this is the normal force. As we said, if the normal force increases, the frictional force increases. And then this is the frictional force. Okay? All right. So let's go back to our static and kinetic. I promised we would. This static friction is equal to mu times my normal force. But in particular, since we have two different types of friction, I'm going to put a little script, a subscript, S, for static. So my static friction is equal to mu S times the normal force. That's not entirely true, because there's actually an inequality here. Now imagine that my static frictional force is 10 newtons, and I push down on this, and then I pull with 10 newtons. What am I going to cause it to do? If I pull with a force that exceeds the frictional force, what is the ruler going to do? It's going to move. So I'm going to cause a net force that's greater than 0, and that will cause it to accelerate. And if I cause it to move, then is static friction still relevant? No, because static friction is only between stationary objects. Okay? So if I move my object, if I exceed the static frictional force, then there's no, then the static frictional force doesn't apply anymore. So to say this more correctly would be to say that the static frictional force is less than or equal to mu S times the normal force. That means that your static frictional force has a maximum value, and once you exceed that maximum value, it causes it to move. So we'll go back to our ruler. I push down on it. I cause, say, a maximum static frictional force of 10 newtons. If I pull on it with, say, 2 newtons, I don't cause it to move. If I pull on it with 3 newtons, I don't cause it to move. Right? It stays where it is, so my static frictional force is what it is. So if I pull on this with 2 newtons, then what is my static frictional force? If the maximum is 10 newtons, and I pull on it with 2 newtons, what is my static frictional force? 8? No, not 8. No. What are you thinking? Let me draw a picture. I'm going to go to the next page. I'll come back to this page. I want to go to the next page. So imagine that I have this object. It's on a surface. The maximum static frictional force is equal to 10 newtons. All right. If I pull on it with a force equal to 2 newtons, don't write this down. Don't write this down because this is not correct. But what if my frictional force over here was 10 newtons? What would happen? I got a 2 Newton force here and a 10 Newton force here. What would happen to this block? It would move to the left. But friction isn't going to cause it to move. Friction always opposes the motion. Right, so that means that my frictional force, since it's not moving, this frictional force has to be, everybody says, 2 newtons. Right? But if I say pull on it with 3 newtons, then this is 3 newtons. If I pull on it with 4 newtons, then this is 4 newtons. On and on until I get up to 10 newtons, and when I exceed 10 newtons, then it starts to move. I push on this with 50 newtons. the frictional force is also 50 newtons. And I keep pushing, pushing, pushing until it moves, and then the frictional force isn't at play anymore. Y'all follow what I mean? The frictional force is a moving value, and it depends. It has a maximum, which is equal to that coefficient times the normal force. And once you exceed that maximum, your static friction is no longer relevant. That you move into the realm of kinetic friction. All right, so kinetic friction then is between sliding objects. One point I want you to know, well, this is similar to what we had with kinetic static friction. In this case, Fk is equal to mu k times my normal force. That coefficient of friction times the normal force, just like for static friction, but we don't have all that business with the inequalities. It is what it is. And no matter how fast you go, your kinetic friction basically stays the same. Now that's not all the time true. Like if you go really fast, things heat up and your kinetic friction can change. But as far as we're concerned, it's going to stay the same. One interesting thing about static versus kinetic friction that you can try when you leave here to demonstrate to your friends is that static friction always exceeds, always, most of the time, exceeds kinetic friction. The frictional force that's a static frictional force is almost always bigger than a kinetic frictional force. Between given two surfaces, that static frictional force is almost always bigger than a kinetic friction force. Example, y'all think of an example where that comes into play? Where? Where? All right. Big heavy piano in your house or whatever, big piece of furniture. All right, you try to move it. What happens? What's that? Probably not going to go anywhere, yeah. But after you get it moving, is it harder or easier to keep it moving? It's easier. So whenever you're trying to push the box, right? And you try and you push and you push and push, and it's really hard until finally you get it moving, and then it's a lot easier. I can even feel it with the desk, that it's a lot easier to move, right? So you probably witnessed that before, that it's hard to get something to move, but then after you get it moving, it's easier, considerably easier, noticeably easier to keep it moving. You can try that. Another thing that I want you to try, that you probably never witnessed before, because you hardly ever stop at a stop sign, all right? Like you might sort of stop at a stop sign, but you don't ever come to a complete stop. So when you're going out on Maywood or wherever you leave campus, as you're headed out, I want you to come slowly to a complete stop with your car or your truck or whatever. All right. What happens when you come to a complete stop? Right. Yeah. You lurch forward a little bit, and then you go backwards just a bit. And the reason is because there's a difference between static and kinetic friction. Static friction is bigger than kinetic friction. Really, the reason there's a difference between the two. And so as you're going along and you're put on your brakes, what frictional force is at play there? Static or kinetic friction? You know how your brakes work? There's a rotor inside your wheel, a metal disc, and it has these things that clamp down on it, or sometimes there's a drum, like consider a disc. You have these brake pads that clamp onto it and cause the wheel to stop. What is the force between the brake pads and the rotor? Kinetic or static friction as it's moving, as you're driving forward? That's a kinetic friction force because it's moving. The two objects are moving with relation to one another. But then as you stop, what is the frictional force? What holds you in place? It's the static friction force because they're not moving. Right? So you have this discontinuity between kinetic friction and static friction. That's what causes you to lurch forward. Are y'all going to try that when you leave? Or are you just going to fly right through that stop sign? Y'all try it. It's pretty dramatic, actually, when you notice it. And then you'll notice you're going to stop at every stop sign for the rest of your life just to witness that phenomenon. Okay? All right. All right, so that's frictional forces. You need to know it's proportional to the normal force. If normal force increases, frictional force increases. You need to know it's proportional to or changes with the type of surface, and that's characterized by this three-letter mu, the coefficient of friction. You need to know kinetic is generally smaller than static friction, and this whole idea about static friction, how it's sort of a moving value depending upon what forces it's responding to. I like friction. You know, there's something else interesting about friction. Y'all care? You don't have to write this down, but it's very interesting, I think. You have two types of friction, macroscopic and microscopic. Don't write this down. I'm not ever going to ask you this again, unless you just think it's very interesting. Put a little thought bubble around it. Macroscopic is the friction between large-scale surfaces, right? So if I have two surfaces that are encountering friction because of, you know, whatever, things that are rubbing against one another, that's macroscopic, right? So if I imagine I have really rough surfaces, that's called macroscopic friction. But then, as you might expect, if I smooth those surfaces, I sand them down and I start smoothing them, what happens to the frictional force? Does it increase or decrease? Decreases, because I'm decreasing that coefficient of friction. I'm changing the surface. And so if I were to plot, say, the frictional force with the smoothness, and the frictional force will go down as the smoothness increases, as you might expect. But something really interesting happens when you get objects that are extremely smooth. What happens as they get smoother and smoother? Your friction starts to go back up again. You might know why. So what happens as you get them smoother and smoother and smoother, eventually it's going to go back up. Now this is macroscopic, and this is micro. How could you explain that? Why would the friction begin to increase? Why am I raising it? Well, what are you getting closer to one another as you smooth those surfaces? It's getting closer and closer and closer. Well, materials are made up of what? Basic building block of atoms. Atoms, and then atoms are made up of charges, protons and neutrons and electrons. So what's happening is, as you get them smoother and smoother, like literally the electrons are getting closer, the atoms are getting closer and closer, and there are charges there. And so what happens is, you begin to have electric forces coming. Like the atoms are actually attracted to one another. That's pretty cool, right? Like you would never expect that, and I think it's funny. All right. Let's do some concept tests, and then we'll move on to rotational motion. Okay, a book is lying at rest on a table. The book will remain there at rest because which of these? The book has too much inertia. There are no forces acting on it at all. It does move, just too slowly. That's not right, by the way. There is no net force on the book. There is a net force, but the book is too heavy to move. Which of those explain why a book is lying at rest on a table? Okay, please ask your neighbor what they think. Y'all like my shirt? My wife got me this shirt. Y'all like this shirt? Like, I know that y'all been wanting to say something about it. Yeah, she actually bought the shirt and she kind of stitched it that place. Pretty nice, isn't it? It was our anniversary. She got it for our anniversary. Alright, let's see. You ask your neighbor what they thought? Oh, good. We're still sort of split between two answers, evenly split, and one of them, of course, is wrong. I'm going to go and tell you what those two answers are. You guys are split between A and D. So why don't you sort of come amongst yourselves and figure out which it is. Both of them seem reasonable. Right. Almost everybody has either A or D. Find somebody who has a different answer from you, huh? Ask around and see if they can convince you. We're sort of moving in the wrong direction right now. The class is shifting. I'm losing you. All right, I'm going to stop in about 8 seconds. I'll stop at 250. We're still sort of split evenly. Okay, the answer is D. All right, listen, a couple things wrong with this one. Or one thing wrong, really. There is a net force. That's really the incorrect statement there, because if there is a net force, there has to be acceleration. That's from Newton's second law, the law of acceleration. If I have a net force, there will be an acceleration, no matter how much inertia it has, no matter what the mass is. Even if it's just a tiny little bit of acceleration, you'll still have an acceleration. So that's the problem with part A. Here, B, there is no net force on the book. That's the correct answer. I'm really proud of you, though, because hardly anybody, a couple people maybe, did not put B, which is not correct, that there are no forces acting on it at all. But that's sort of the common mistake that people make, is they put B. There are, of course, all sorts of forces acting on the book. There's the gravitational force, there's the normal force. There are forces within the book, like intermolecular forces between the atoms and the molecules. So there are lots of forces, but they all cancel one another out, so that there is no net force on the book. So I'm very proud of you for that, but hardly anybody put B, which is not correct. And A is not correct, because if there was a net force, there would be acceleration. A hockey puck slides on ice at constant velocity. What is the net force acting on the puck? Is the net force more than its weight, equal to its weight, less than its weight, more than zero, depends on the speed of the puck, or zero? This is the net force. Let's not forget our Newton's second law, right? Newton's second law says that the net force is equal to the mass times the acceleration. So if we have a net force, we will have an acceleration. And the opposite of that is true. If we have an acceleration, we have a net force. If we have no acceleration, we have no net force. Can I repeat what I just said? Remember Newton's second law, right? F equals ma. If our acceleration, if we have no acceleration, we have no net force. Right? F equals ma. F net, or net force, equals mass times acceleration. What is our acceleration of this puck? It has a zero acceleration. How do we know that from the words? Right. Acceleration means your velocity is changing. Here we have a constant velocity. So that means that the net force then equals ma. What is our acceleration? If our acceleration is zero, then what is our net force? 0. Right. Okay. I'm going to go ahead and stop. Okay, E is right. If our acceleration is 0, constant velocity, that means that our net force is 0. There are forces, of course, acting on the buck. Gravitational force, there is, and the normal force are acting. But there are no forces acting in the horizontal directions. It's moving at a constant speed. Let's try this one. These type questions, by the way, won't be on the reading quiz. This isn't really from your reading. Newton's laws and stuff is, but these are good to help you prepare for the exam, which is coming up in a couple weeks. And I'll post all these PowerPoints online so you can have them to look at. And of course the screencast online as well. All right. You know, they ask these questions. These questions are sort of part of a larger assessment that they asked them. They asked a number of years ago an exiting class at Harvard, an exiting physics class, the students that had finished the physics class in Harvard. And they expected the students to do really well because, you know, they're Harvard students or whatever you're going to say. But the students average like 30% on these tests, or even less in some cases. So, that said, y'all are making a very common mistake, is that many of you have put a net force acted on this book, and for good reason, right? The book seems to slide off the seat, so you say, well, it's accelerating off the seat, so it must have a net force, right? But the fact is, the book isn't. Don't think of it as the book sliding off the seat. Think of the seat as stopping, right? Because the bus is moving along with the book on the seat, and then the bus stops, and the book just keeps moving forward. You follow what I'm saying? So you can think about it in a different way, not as the book moving forward all of a sudden, because the book's been moving forward all this time as the bus is traveling along. But you think instead of the seat all of a sudden stopping. Okay? And so with that then, why does the book slide forward off the seat? Okay, now a lot of you are putting C, which is also not correct. All right, so the book doesn't remain at rest, right? The book does move. It's really the bus that's stopping. What causes the book to move? Why does the book? How can you explain, thinking about Newton's laws, his law of inertia, his law of acceleration, how can you think about those laws and describe why this book moves? All right, now we're just sort of grasping for straws, I think. Is anybody really confident about their answer? Who's confident? Nobody is? Okay, well, I'm going to stop it then. I'll explain. All right, B is right, though. All right, so no net force acted on it. This goes back to Newton's first law, that an object that is in a state of motion will continue in that state of motion unless acted upon by an outside force. So in this case, the book, which is sitting next to you in the bus seat, it is moving along at a certain speed, and then when the bus stops, no force acts on it to keep it from stopping as well, and so it just continues on moving. So it's a nice demonstration of the law of inertia, which is Newton's first law. That is that an object in a state of motion, whether it's moving or not moving, will continue in that state of motion unless a force acts upon it. And in this case, the book was in a state of motion. That is, it was moving forward with the bus. And then the bus stopped all of a sudden, and the book, since there were no forces acting on it, slid off the seat. Or there weren't enough forces acting on it to cause it to stay on the seat. Yeah? Yes? Sort of? It might take a little while to sink in. These ideas are, thousands of years old, and it's very hard to sort of rewire those synapses in your mind. All right, you kick a smooth, flat stone out on a frozen pond. The stone slides, slows down, and eventually stops. You conclude that which of these? Right, doing a very good job. I'm going to stop at 55. 55. Okay, very good. The stone slows down. That means its velocity is changing. That means it's accelerating. Anytime you have a changing velocity, we call that acceleration. And if it's accelerating, that means that a net force has to be acting upon it. No net force acted on the stone. Now, if B was true, no net force acted on the stone, what would happen to the stone? It would keep going on forever until a force acted on it. Okay? And A, the force pushing the stone forward finally stopped pushing on it. No. No, that's just not true. Sorry. All right. Let's see. Give me just a second. I want to look at something. I think I have the wrong file here. Okay. We'll do a few more of these. Oh shoot, what happened last thing? Okay. Consider a card on a frictionless table. Once the card has been given a push and released, what will happen to the card? I push a card, it's on a frictionless table, what happens to it? Now notice the force here. You're applying a force right at the beginning, but then you're no longer applying the force. You push it and then you let it go, and then it goes on how it will. So the force, you're not continuously pushing the car. And this is a frictionless table, so there's no friction at all. I'm going to stop at 108. 108. D is right. I have this object, I give it a certain speed by pushing on it with a force, and then I take away that force. It's going to continue at that speed unless there's another force that acts upon it. And currently there is no force acting upon it. All right, what would we have to do to give this cart continuous acceleration, constant acceleration? Do we just push it harder before releasing it, push it longer before releasing it, push it continuously, change the mass of the cart, or it's just impossible? Stop at 45 seconds. Y'all are getting better at these. You're starting to get the Newton's law stuff a little bit better. All right, I'll stop at 50. All right, C is right. In order to have constant acceleration, I have to have a constant force, always at work. Let's skip this. We're going to skip these two. Okay, I think we'll stop there. I have a lot more than I wanted, actually. I'm going to go through and I'll edit them and I'll put them online for y'all to see. Our exam is coming up. When is the date for the exam? Somebody remind me? The 24th of this month. Oh, I mean of February. So we have a few weeks till the exam. But that'll be a good place for you to study, to look at those, the PowerPoints I'll put online. And then, of course, reading your book and then going through your notes. So if you're one to be studying for your test right now, which I encourage you to do so, that you're always sort of reviewing and keeping on top of things, I would recommend that you do those things. When I make these available to you in the next couple of days, please print them out. I print them 6 to a page, and then you can fold them over and you can sort of quiz yourself on them, have the questions on one side, the answers on the other. I can get your friend to quiz you on them. And then go through your notes. If you miss a day, of course, remember the screencasts are online, so you can catch that. And read your book. A lot of your questions will be straight from the book, like the reading quizzes. Reading quizzes are good practice. All right, you ready to take the reading quiz? It shouldn't take you 20 minutes, but just in case. I won't always give you this long. I'm just sort of at a stopping point here. I do want to show you something, though, about the reading quiz. We have a particular type of form that we're using, so it's a multiple choice form. It looks a lot like this, right? It looks a lot like this form, so you'll pick your answers, and then you'll bubble them in the appropriate bubbles. Y'all know how to do that, right? But the thing that students often have trouble doing in my classes is getting their N number correctly. Y'all know your N number. It's a 0. It's an 8-digit number. So say it's 000724331. All right. Notice here that on this, you might not be able to see actually, but when you get your paper, you'll see that the first column here is zeros, and then the other columns are 1 through 9. So mistakes that people make, and it's really a pain in the rear for me because then I have the wrong number for your name, for your grade, is that when you bubble these, you bubble zeros in the first column, but ones are in the second column. Y'all follow what I mean? The bubbles start at 0. And so having said that, I know there will at least be one person that has a 1 in their N number, and they're going to bubble their 1 in the first column. So when I read it, it's going to read it as a 0, not as a 1. Y'all follow what I mean by that? So think to yourself, do I have a 1 in my N number? Who is that? Who has a 1 in their N number? Okay, make sure you bubble that 1 in the second column, okay? Because that's a common mistake that people make. All right? The quiz is multiple choice on the front, but that form is on the back here. All right? I do want y'all to sort of spread out, so you can just sort of go in your rows and spread out all the way to the back. Please. Thank you. And then I'll hand out the quiz. We'll do that every time we have a quiz. So, okay, good practice. Give yourself some space. Just a quiz, okay? But if I check, if you're looking on somebody else's paper, it's going to be a 0 for a quiz, and that won't be a drop grade, okay? You can use a pen, but if you mess up the bubbling, it's going to be hard. can go when you're done. Make sure you bubble your answers on the back. That's what I'll use for your answer, okay? Who had the clickers with issues? Jason was one of them.